As we have discussed in the previous lecture, a quick revision. All the tests of significance, including chi-square test, are used for comparison between two or more groups. We compare whether the difference between the two groups is just by chance or there is an actual difference between the two groups due to any reason. So, null hypothesis assumes that the difference between the two groups is not real, that is, it is only by chance. All the tests of significance, including the chi-square test, they calculate the probability of null hypothesis being true. The magnitude of this probability is expressed as the p-value. A cutoff p-value of 0.05 has been decided on. So, if the probability of null hypothesis being true is less than 0.05, we say it is too low, and hence the null hypothesis is rejected. And we say that the difference between the two groups is significant. That is, the alternative hypothesis is true and not the null hypothesis. But if the p-value is 0.05 or more, we accept the null hypothesis and we say that the difference between the two groups is not real but only by chance. And how do we arrive at this p-value? P-value is calculated by using the appropriate test of significance. So, if a test of significance has been applied to a study where it is not appropriate, the p-values will be rejected by the reader. So, we have to be careful that the appropriate test of significance has to be applied to the. We have already discussed about the qualitative and quantitative types of data in the previous lecture. Commonly used tests of significance for qualitative data are standard error of difference between two proportions and chi-square test. In short, qualitative data is the data where the subjects with the attribute can be counted. The attribute is either absent or present in the subject, and hence qualitative data can be expressed as proportion of participants who have the attribute, or ratio or rate or percentage. Examples are 10% of the obese, they developed CHD, coronary heart disease. 5 out of 146 vaccinated got the disease versus 53 out of 150 unvaccinated. So we need to compare 5 out of 146 versus 53 out of 150. We compare the two proportions. So the terms incidence, rates and prevalence, etc. can be applied to qualitative data only. In this lecture, we will discuss about the chi-square test. The steps in the chi-square test lead to the calculation of the value of chi-square for the given data. This value of calculated chi-square is then referred to that in the chi-square table, from where the p-value can be calculated, can be deduced. Chi-square test can be applied on qualitative data, sample that has been chosen randomly. The lowest observed frequency in all the cells should be 5 or more, and none of the observed value should be 0. Advantages of chi-square test over the standard error or difference between two means are that chi-square test is equally applicable to small samples as well as large samples, and the test can be used even when there are more than two categories, where the standard error of. We will first discuss the steps in brief and then in detail with an example. So, steps in brief, the first step is to make a contingency table mentioning the observed frequency in all the cells. Second step, we determine the expected value in each cell. The expected value as if null hypothesis was true. Null hypothesis assumes that the data is distributed due to chance alone, and hence the proportions in both the groups or more than two groups should be the same for all the samples. And what should be that proportion? We arrive at this proportion by taking the combined proportion of all the groups. That is, total individuals, participants who have the attribute divided by total participants, combining all the groups. So that proportion is applied to all the groups. And the expected number according to that proportion is calculated for all the cells. Step 3 is we calculate the difference between the observed value and the expected value for each cell. In next step, we calculate the chi-square value for each cell, that is observed value minus expected value, the whole square, and divide this by the expected value. This is the chi-square for the cell. In the fifth step, we sum up all the individual chi-square values, that is the chi-square values of all the cells are added up, and this gives the value of the chi-square for the whole table for this study. Sixth step, we determine the degree of freedom. Degree of freedom is calculated by number of columns minus 1 multiplied by number of rows minus 1. So C minus 1 into R minus 1, where C is the number of columns and R is the number of rows in the given table that we have constructed. Seventh step, we refer to the chi-square table and note the chi-square value which is given in the table against the calculated degree of freedom and under the p-value of 0.05. This is demonstrated in the next slide. If our chi-square value which we have calculated is higher than that we have noted in the table, which is against the given degree of freedom and below the p-value of 0.05, if our chi-square value is higher, we say that p is less than 0.05 and the difference is significant. This slide we will demonstrate how to refer to the chi-square table. We can see the contingency table below, where we have entered the values in the given 4 cells. The degree of freedom has been calculated to be 1. Why? Because we consider these 4 cells which contain the actual data. You can see the remaining cells have only totals in them. So the 4 cells are distributed in 2 columns and 2 rows. The degree of freedom is 2 minus 1 into 2 minus 1, that is 1 into 1 and 1. And chi-square is calculated to be 10.89. How? This is what the remaining lecture is all about. How do we calculate the chi-square? Here we will show you the chi-square table above our contingency table, where the degrees of freedom have been listed on the left side and p-values on the top. Now degree of freedom has been calculated to be 1, so we look against the degree of freedom 1 below the p-value of 0.05. The chi-square in the table is 3.84. Ours is higher than that. Next, we see 0.02 p-value. The chi-square in the table is 5.4. Ours is higher than that also. In fact, when we look under p 0.001, the chi-square given here is lesser than our calculated chi-square value. So our chi-square is higher than 10.82 also. That means the p-value is less than 0.001. So not just less than we will study the steps in more detail by using an example. The first example is association between family history of breast carcinoma and incidence of breast carcinoma in women. Is there an association between the two? A case control study was conducted where 250 cases were studied and 300 controls were studied, and it was found that 20 out of 250 cases had a positive family history of breast carcinoma, against 6 out of 300 controls had a positive family history of breast carcinoma. So apparently it seems that a higher proportion of cases have a positive family history of breast carcinoma in their family. But again, the null hypothesis says this difference, however big it may be, is due to chance alone. So we proceed on to apply the chi-square test to calculate. Step 1 is construction of a contingency table. So this is a table. We enter the number of first row, we enter cases, second row we enter controls. Now in the table we enter the totals. The total number of cases was 250 and the total number of controls was 300 and the total number of participants was 550, both cases and controls. Now we enter those numbers which have a positive family history. 20 cases had a positive family history, 6 controls had a positive family history. So the remaining 230 cases did not have a family history of breast carcinoma and the remaining 294 controls did not have a positive family history. So this is the final contingency table. In step 2, we determine the expected value for each cell. Expected value as if the null hypothesis is true. So applying the proportion from the totals, we calculate the expected value against each observed value. First, we arrive at the combined proportion. So the total number of people who have a positive family history are 20 plus 6, that is 26. And the total participants, that is both cases in control, is 550. So 26 participants out of 550 participants have a positive family history. That is 4.7% of women in the total pool have a positive family history. So the expected percentage should be the same in all the groups, that is both cases and control, that is 4.7% each if null hypothesis is true. So the expected number of cases with positive family history will be 4.7 divided by 100 into number of cases, which comes out to be 11.75. This is the expected number for cell 1. Similarly, expected number of controls with positive history should also be 4.7%. So 4.7 divided by 100 into number of controls, 14.1. Similarly, expected number of cases without family history is 250 minus 11.75, 238.25. And the expected number of controls without family history will be total controls minus those the expected value for to having positive family history. So 280.85.1. Now we enter these values. Step 3 is to calculate the difference between the observed value and the expected value for each cell. So we calculated the expected value and we have entered the observed value. In the second table below, we have calculated the difference between the observed and expected values for each of the 4 cells. In step 4, we calculate the chi-square for each cell. The formula for chi-square is difference between the observed and expected value squared, and this squared value is divided by the expected value. So the first table shows the differences between observed and expected value that we calculated before. Then the chi-square calculation for each cell, and the third table gives the chi-square value for each cell. Step 5, we sum up the individual chi-square values of all the cells, and the sum is 11.06. This is the chi-square value for the entire table. Next step, we determine the degrees of freedom is number of columns minus 1 into number of rows minus 1. So that is 2 minus 1 into 2 minus 1, 1 into 1, 1. So degree of freedom has been calculated to be. And in the final step, we refer to the chi-square table to calculate the p-value. In the chi-square table, we look against the calculated degree of freedom and under p-value of 0.05. We previously noted that against degree of freedom of 1 and p 0.05, the table chi-square value is only 3.84. And so any value above 3.84 with the degree of freedom 1 would be significant. Our chi-square value is 11.06, way more than 3.84, and hence p value is less than 0.05. In fact, the p below 0.001 at degree of freedom 1 is also much less than our calculated value of 11.06 we noted in the previous slide. And hence, the difference between the percentage of women with positive family history is significant. So actually, the cases have a higher percentage with positive family history, and we conclude that the positive family history of breast carcinoma and incidence of breast carcinoma are associated. The second example we will consider when the groups are more than 2. Association between maternal age at conception and the incidence of Down syndrome in the offspring. 10,000 pregnant women in each of the given age groups were followed up till delivery, and the delivery of a baby with or without Down syndrome was noted. The results have been shown in the following table. The first step is to construct a contingency table. This is the given data, that the age groups, total number of women in each age group, and number of babies born with Down syndrome. 5 in 20 to 25 age groups, 6 in 26 to 30 year age group, and so on. In the contingency table, we make another column where we enter the delivery of a baby without Down syndrome. So in the first age group, 5 women delivered a baby with Down syndrome and 9995 did not have a Down syndrome baby. Similarly, we enter for all the groups and then we enter all the totals. This is the contingency table. After constructing the contingency table, we determine the expected value for each cell. For this, we pool all the participants and the incidence of Down syndrome. Total of 63 babies were born with Down syndrome out of 50,000 women who were followed up. So the incidence 63 divided by 50,000 into 100 was 0.13%. And similarly, the incidence of no Down syndrome in total women was 99.8%. That is 99.8% of all the women in all the groups together gave birth to a baby which did not have Down syndrome. So the expected value in all the cells with Down syndrome column would be 0.13 divided by 100 into 10,000, because the number in each group is 10,000. Otherwise, you will multiply with the number of individuals in each group. In this case, the number of individuals in this group is 10,000 is equal. So the expected value in all the cells under the Down syndrome column would be 13 because the total is same. Similarly, the expected value in all the cells under the column with no Down syndrome would be 99.8 divided by 100 into the number in each group, that is 10,000. 99,980. So here we have entered the expected value in each cell against the observed value. Step 3. We calculate the difference between the observed value and the expected value in each cell. First cell 5 minus 13 minus 8. Second cell 9995 minus 9980 15, and similarly we calculate for all the cells. Step 4. Calculate the chi-square value for each cell. So each difference is squared and divided by the expected value of that cell. So first cell had a difference between observed and expected value as minus 8. So minus 8 squared divided by the expected value, which was 13. So chi-square for the first cell is 4.9. Similarly, we calculate the chi-square for each of the cells. Step 5 is calculation of the chi-square value for the entire table. For this, we sum up the individual chi-square value of all the cells. We add up, the sum comes out to be 24.66. This is the value of chi-square for the whole table. Step 6. Determine the degree of freedom. Number of columns minus 1 into number of rows minus 1. In the given table, we have 2 columns and 5 rows. So 2 minus 1 into 5 minus 1, which is 1 into 4. Degree of freedom is 4. Finally, we refer to the chi-square table. Under the p-value of 0.05 and against the calculated degree of freedom. Here we see that the value against degree of freedom 4 and under p-value of 0.05 is 9.488. Our chi-square value is 24.66, which is higher. In fact, the table chi-square value below p 0.001 against degree of freedom 4 is also only 18.465, and our value is 24.6, higher than this, so our p-value is less than 0.001 also, and hence the difference is highly significant. Hence, maternal age at conception is found to be related to the incidence of birth of Down syndrome in the present study. For situations where the contingency table is 2 by 2, that it has 2 rows and 2 columns, excluding the totals, of course. In this given table, A plus B is the number of cases out of which A have the risk factor, and C plus D is the number of controls out of which C have the risk factor, and N is the total number of participants. So the chi-square value in this kind of table can be calculated directly using the formula which is given below. Hence, for a 2 by 2 table, the calculation of expected number can be bypassed and chi-square calculation. However, if any of the cell frequency in the 2 by 2 table is less than 5, then we need to modify the formula as below. Here, AD minus BC surrounded by two straight lines is called as modulus AD minus BC, which means whether the result is negative or positive, we will consider only the positive value. And this is known as Yates correction of the formula. But remember, if any of the cell has a value of 0, then chi-square test cannot be applied even with Yates correction. Even if the table is higher than 2 by 2 and any of the cells frequency is 0, chi-square test cannot be applied. If possible, you can merge 2 or more classes to arrive at a value more than 0.